In this paper, we studied the role of modeling theory of mind in few-shot language coordination problems. In the referential game, a speaker describes the target in natural language, and the listener picks out the target among various candidates. The traditional setting uses the same speaker and the listener in both training and the test phases, which is often called self-play. While humans communicate with a larger community by coordinating with different and novel interlocutors within short conversations. This ability, future language coordination, has been less studied by the previous research. Different from self-play, we require the speaker to train with at least training listeners and test with another set of agents, the test listeners, which are drawn from the same population as the training listeners. Developmental psychology argues the importance of theory of mind in human language coordination. Theory of mind is the ability to understand and act upon others' mental states. Drawing inspiration from theory of mind, we study the following research question. Can an agent equipped with a model of the theory of mind quickly adapt to a listener's language in a few-shot language coordination game? Here we show a demonstration of interaction between speaker and the listener in the navigation setting. After observing the goal, the speaker gives a task-level comment to the listener, which appears to understand the comment by producing three correct actions in a row. After each action, the environment provides the observation to both the speaker and the listener. Based on this history, the speaker is fairly confident that even without giving further comments, the listener can still finish the game. However, the listener goes to the microwave instead of the fridge. The speaker has to change his belief and give action instructions. To create populations, we first build multiple corpora with different language variants. And then from a dirichlet distribution, we sample a distribution of training data for each listener. Based on this distribution, the training data are sampled from various corpora. Through training on this training data, the listeners are different from each other in terms of the language they speak, but the whole population follows a common distribution. In different games, the distinction between corpora can be different. We experiment with two kinds of games. The first is multilingual referential games, where the corpora are MS Google captions translated into 10 languages. And the second is off-world task navigation, where the corpora are of different command levels, from the task level to action level. After the population of listeners are pre-trained, we can train the tone model with them. The tone model uses the same architecture as the listeners, but its parameters are trained using model-agnostic meta-learning. At each episode in an epoch, the parameters of the tone model are updated to predict the listener's response with inner loops. The initial parameters are trained via outer loops after the episode. To select the best instructions from the candidate pools, the tone model is used to choose the candidate, maximizing the probability of the correct action. Empirical evaluation shows that the speaker, with the help of the theory of mind, achieves better success rates compared to vanilla image captioners, rational speech app, and even the model that learns an average of a population without adapting to individuals. This shows that tone model successfully adapted to individual listeners in multilingual referential game in just 20 rounds of interaction. We get similar results in off-world task navigation. We found that our model achieves much higher gain points than random speakers at the same cost. The success of our tone model hints at the importance of modeling communication as a social pragmatic process. Thank you for listening.